Um, Today, we're going to talk about the results of some analysis we've been doing on Army sustainment data. We've been collecting data from all Army programs doing sustainment. We have a data set that has 192 programs in it, which represents the majority of the programs in the Army that are doing sustainment. Our definition of sustainment includes those that have passed milestone C. So basically what we say is as soon as you get the first release out there, whether it's for a demo, whether it's for a formal test, whether it's for an early checkout in the field, or for a full delivery, you have to start sustaining it. You have to at least do the security updates, and you may have some bug fixing that you need to do. So in the Army, that includes folks that are doing both with the traditional maintenance, which is the OMA-funded pure maintenance that happens after delivery, but it also includes the PEO-led work that happens after milestone C. And as we're switching to more agile and agile-like systems, a lot of programs are moving to more of a DevOps rhythm where they are doing some new work as well as sustaining programs. And the data that we have in this data set includes all of those data, all of that data in it. So based on that data, we started with doing basic regression analysis, and then we've sort of taken it to the next step with what we're going to talk about today, where we're actually looking at improving the regression analysis we're doing and using multiple methods and doing some machine learning and some modern regression methods. So Christian and Kim will talk more about what we did with this data set and the analysis from that. There is a report that's available on the ICEAA website and also a report on sort of two other aspects of this work, including the basic regression analysis we did and some annualizing of data that we did this year, as well as some work we did on I can't even think of the topic. Another set of data we did. So there's actually 3 reports out there on the ICEAA website if you want to go and learn more about this analysis. And with that, I'm going to turn it over to Christian and Kim and let them tell you about the details of this.
Okay, and then Cheryl, I guess that also includes your paper from last year too, right? So your best paper from last year.
Yes.
Also has some information about this. So today we're going to talk to you about some work we've done with Cheryl and PGA and Brad Clark and James Doswell on the software sustainment and leveraging the wisdom of crowds, which basically using multiple methods enhances predictive accuracy. If there's one thing you want to take away from this presentation, it's using multiple methods will enhance your predictive accuracy. One of the principles of in prediction is you don't want to make things too complicated in general, but and using multiple methods is more complicated, but they found that paradoxically, the more methods that you have, if they are suitably diverse or certain conditions, the more accurate you get, even though what you wind up with is slightly more complicated. So if we go to the next slide, Kim. So building cost estimating relationships, let's talk about that a little bit. And the Department of Defense, NASA, Aerospace, a lot of different data sets that we use. We typically observe non-linear relationships between cost and, are sometimes called covariates or sometimes called cost drivers. These relationships like weight, technical parameters, programmatic parameters. A common way to handle this is to take a log transformation. The power equation is pretty common, which is y equals a times x raised to the b power is pretty common. So that can be linearized, and you can apply linear regression to that if you take a log transformation. It's commonly used, but that's a little bit dated in certain senses. There are better methods out there for doing that. One of the key issues with log transformed ordinary least squares regression is bias. You're estimating at the median rather than the mean, so your estimates on average will be lower than average. There are some alternative methods, and I think Cheryl alluded to this. There are modern regression methods that are unbiased, and there's also machine learning methods. A lot of machine learning methods are used for classification, but they also can be used for prediction of numerical values like cost. Go to the next slide. Yeah, so we can go to the next slide. Okay, so yeah, so combining estimates, choosing the best estimate. Suppose that you have multiple estimates. How would you pick the best estimate? And is there any benefit in combining these estimates? That's one of the things we'll talk about. And so in statistics and machine learning, this is called an ensemble approach. Okay, next slide. And kind of relate this back to a little story about the wisdom of crowds effect. Combining estimates is better than using the single best model. So that's kind of interesting and somewhat counterintuitive. You would think that, so if you were, for example, if you were going to hire someone to do some work on your house, you would probably try to find the single best person that would provide you a reasonable price. Imagine instead that you were to go out and hire a bunch of people and then kind of think that overall the average result would be better. That doesn't really seem to make sense. If you were going to hire a band, you want the best musicians rather than some collaboration of average musicians. But it turns out in this case that combining even less than the best models is better than using one single best model. You see this quite a bit in weather. For example, with hurricane forecasting, you will see where you kind of see a bunch of different results of a bunch of different models out there, and kind of these little spaghetti noodles are out there, and then they kind of show what the average is. And usually the average is better predictor of where the hurricane will head than any single model. Okay, next slide. And The Wisdom of Crowds is a book by James Sarawicki where he talks about this phenomenon. If you need a large group and you need a diverse group, and that asking to make decisions affecting matters of general interest. These are somewhat matters of cognition, is one of the cases. The group's decisions will generally be better than a single individual, and the average forecast is better than the single best forecast. Now, the three keys to that are the forecast should be independent. So one of the pitfalls in consensus decision making is sometimes groupthink. Everyone gets together in a room and one single individual dominates and convinces everyone else to use his idea or use his forecast, and that's not getting multiple people together is not going to help in that instance. You want them to be independent. You want the forecast to be independent of each other. You want them to be diverse. They could be using different methods. They could be using slightly different data sets, and you want some decentralization. So you don't want some central authority that is going to influence them. So that's kind of also related to the independence. Okay, next slide. So here's an example, famous example that's in Sarawicki's book is Francis Galton, who was a statistician. He's actually the person that coined the term regression, which actually comes from regression to the mean. He observed a competition to guess the weight of an ox at an English country fair in 1906. And his hypothesis was that the average person was not going to produce a very good forecast. So he went in with an open mind about what he was going to see, but he had a hypothesis about what he expected to see. There were 800 people, it was a diverse group, all kinds of folks, some farmers, some butchers, others with no in-depth knowledge of farming or livestock. And so he got the statistics afterward to see how close the average was. And the crowd guess was within 3 pounds of the actual weight, or actually 1 pound, within 1 pound of the actual weight, 1,197 pounds. That is 1 pound less than the actual weight. I've tried this experiment out in a couple of different settings, guessing the number of pieces of candy in a jar, that kind of thing. I've done that a couple of times, see what the results were. And these were smaller data sets. So in those particular instances, we're talking about maybe a couple dozen people. The average guess was not as good as the best guess. Also, for smaller data sets, the mean guess was sometimes influenced by an outlier. Both cases I've seen this, I've kind of done this experiment. You would get some pretty wacky numbers. So the actual number was 100, and one person guessed 5,000 another person guessed 10. So you see these kind of wacky numbers. So the mean can be influenced by those. So smaller data sets, the median may be a better option. Next slide. Another example of this is the game show Who Wants to Be a Millionaire. I think it's still on the air. It used to be much more popular as on prime time. Contestants have 3 lifelines they can use to help answer questions. Phone a friend would be like finding the best answer. You would normally try to find someone that was really smart to help you out with that. And you can also poll the audience. That's another lifeline. So phone a friend would be like a single best person. The statistics show that the phone a friend is right 65% of the time, and the audience poll is right 91% of the time. Okay, next slide. Ensemble approach. So that's what we're talking about. Wisdom of crowds. The statistical term for that is ensembles. Multiple methods and combining them. When is this approach useful? So that's what we talked about, ensemble technique. It's a group of items viewed as a whole. You have multiple models. You maybe have multiple equation forms. You may not necessarily have a good handle on what the right equation form is, so maybe averaging those is good. Different methods, different variables. And we're going to discuss 2 ways to combine methods, simple averages and weighted averages. Okay, next slide. Simple averages just take the mean. So that does improve the average of a and you can do it with it doesn't matter if it's a linear equation or like a percent error regression type equation where the error is an absolute value, which is just how far is it, how far is away, or a percentage, what percent, is it 10% off or 20% off, and basically the mean squared error of the average is the expected value of the sums, the average of the error squared. Okay, next slide. And the simple average. So the MSC is always, you can just do a little bit of math here, and basically the average error is roughly, assuming that independence among all the estimates is basically 1 over n. So it's the 1 over n is the, so basically you reduced it by a factor of n. That's a pretty significant factor if you have a lot of different estimates that you're combining. Even if you have 2, you basically cut the variance in half. Okay, next slide. Here's just a simple example of that. We have standard deviations equal to 30% and 50%. The first one has standard percent error. And so basically the variance is 0.09, and the second one has variance 0.25. So that's the squareds. The variance of the simple average is just the average of those 2, and then you divide that by half. So it's not just the average; it's also the average divided by 1 over n, which is better. You have one model that's pretty accurate, but the average, even combining a more mediocre forecast, the average of those 2 is better than the single best model. So we've decreased the uncertainty in our estimate. Next slide. And then for even better results, you can do a weighted average. And the way you would do that is you would take into account the covariance matrix. I'm not going to go into a lot of details here, but I'm just going to note that and if these models are uncorrelated with each other, you're basically just weighting by 1 over the variance. That's called precision weighting, which has a strong connection with Bayesian methods, interestingly enough. I'm not going to go into the math of that there is in the charts in the backup. The details are in there. I think if you go to the website, you download the latest PDF that's in there in the charts, and it's also in the paper. So weighted average has the potential to do that even more. And so in this paper, we're going to apply both those methods to a variety of different regression and machine learning techniques. And then at this point, I'm going to turn it over to Kim to go over the rest of the presentation.
Thanks, Christian. So as Cheryl discussed, we've been supporting their team for the past couple years, and we've had the opportunity to really reap the benefits of all the data collection and the sanitizing efforts that were completed by Cheryl and her team. And it isn't often that we have such a robust data set like the Army Software Sustainment Repository. And for the past 5 years, the Army has done extensive data collection with the use of a questionnaire to collect data on Army software systems. And the questionnaire focuses on collecting important system context information with the emphasis on capturing annual cost and effort data that can be used in the development of cost estimating relationships. And so the database, as Cheryl said, contains data for over 192 Army systems currently in sustainment. And for this analysis, we used one of the trim data sets. And they did trimming based on unit costs, so the total release hours over a number of software changes. And they trimmed the upper 10% and the lower 10% of the data. And the variables included in our analysis are total release hours as a dependent variable, and superdomain, total software changes, and acquisition category as independent variables. So total release hours is the effort required to maintain software in hours. Superdomain is a variable that classifies software systems. So domains include real-time, engineering, automation information, and defense business systems. And I'll note that there were no defense business systems in the data set that we used for this particular analysis. Then we also have total software changes, and that's the most common software size measure across most of the Army systems that we have within the repository. And last, we use acquisition category. We have ACAT levels 1, 2, 3, and some non-program of record data points within the data set. So this is just a little overview of the 6 methods that we use to compare to the log transform ordinary least square model. And so the first 2 are going to be nonlinear, and then we also use for machine learning techniques. So the first nonlinear method that we employed was ZMPE, and that's the 0% bias minimum percent error method, which focuses on minimizing the sum of squared percentage errors. A bias constraint is added for this method when we run it, and we do run this analysis in Solver. Next up, we have Merlin, and Merlin is the maximum likelihood estimation regression for log normal error method, and it's a generalized linear model that is also unbiased. Regression trees, and this is the first of 4 machine learning techniques. It focuses on partitioning data into smaller, more homogeneous groups. Then we have random forest, and which is an ensemble approach actually within itself. It combines multiple regression trees to produce an average, more robust estimate. K-nearest neighbor. It's a non-parametric method that uses weight analogies to predict a numeric target. And support vector machines. And they look at segmenting data and maximizing a margin between classes to yield robust classification. Okay, so this is the log transform OLS model that we developed using our total release hours as our dependent variable. And again, those 3 independent variables that we use are superdomain, ACAT level, and software changes. And superdomain and ACAT level are categorical variables, so we define dummy variables within the data set for these. For superdomain, we have 4 categories, so we assign 3 dummy variables. And for ACAT level, we have 2 groups, ACAT levels 1 and 2, and the rest being the 3 and non-program of records for that. And software changes, that's our continuous variable. Okay, so just to give a little more description of the methods that we use, and for additional details, you can find those within the paper. And so the first 2 methods are nonlinear, and the first is ZMPE, and this method is developed by Dr. Steve Book. And so it focuses on minimizing the percent error while incorporating a constraint that the sample bias is 0. And we calculate this method in Excel Solver. And next up is our second nonlinear method, and that's Merlin. And this is developed by our own Dr. Christian Smart, estimates the mean log normal using the likelihood function. The goal of Merlin is to minimize the pictured function here, where n is the number of data points and theta is estimated as the sample variance of the log space residuals. And this is also calculated within Excel solver. And so next I'll give you just a brief overview of the machine learning methods that we also use in the analysis. And for more information and a little deeper dive into those, you can see our paper and presentation from last year's conference titled Beyond Regression. So regression trees split the data into homogeneous groups, and the resulting graph presents these splits with the use of branches. The tree-based method partitions the data into smaller regions where interactions are more manageable, and the focus is to minimize the error within the groups. And the branches are the decision nodes, and the leaves are the terminal nodes. And so once you get to the terminal node in a regression tree, the splitting ends, and the data points that are left are averaged to provide an estimate of the dependent variable of interest based on the data points within that group. So let's look at a little diagram of a regression tree. And so what it is really like an upside down tree, where the root of the tree is at the top, and that's your full data set. The method asks its first question, and it's a yes or no question. So think of it like if the weight of a vehicle is below 6 tons or above 6 tons. So if yes, it's below 6 tons, then you go one way, no, it goes the other way. And so it continues to split based on a series of questions. So if you follow the tree on the left, a yes or no question is asked, and the group splits into 2 nodes. So you have one terminal node, that green box, and one decision node, the orange box. And then the decision node also splits again into 2 additional terminal nodes. And so this means when all the splitting is done, you end with your terminal node, and this means that your error is minimized and you are averaging the data points that are within those groups. Random forests. They're a great follow-on to regression trees because random forests are a collection of decision trees and is also an ensemble method. The trees have the same layout as a typical regression tree with the node, branches, and leaves, and they also split the same way. They split based on the most important factors in the data set that are minimizing the error. Random forests take the data and generate a large number of decision trees randomly and with replacement. So each singular tree is weaker than the regression tree itself, since the regression tree is based on the entire data set, but all of the trees together in a random forest provide a strong average output and a more robust estimate. Okay, nearest neighbor. So this is a simple technique that uses a feature similarity to predict values of new data points. For your first step would be to calculate the distance between your data points. So for continuous variables, we're going to use the Euclidean calculation, the Euclidean distance, and if you have categorical variables, then you would use the Hamming distance. And once you calculate the distances, each data point is ranked based on the distance, so smallest to largest. Then next, we choose a value for K to select the K nearest neighbors. And a good rule of thumb is to set K equal to the square root of your sample size N, but there's also a method within R that you can use to determine the most optimal value of K based on your data set. And then once K is determined, the outputs for these K nearest neighbors are averaged to estimate the response to the new data point. And our last method, support vectors. Support vector machines method focuses on classifying data in such a way that you maximize the margin between classes. With support vector machines, we want to find a hyperplane that best divides a data set into 2 classes. And the support vectors are those data points that are nearest to the hyperplane, and the points in the data set that, if they're removed, will alter the position of that dividing hyperplane. So our goal with support vector machines is to find an equation that's as flat as possible. That means your coefficients are as small as possible. You want to minimize the residuals that are outside a specified range of the estimate. And then you want a hyperplane with the greatest possible margin between each group. And so with that, it's focusing on trying to group the data points with the most like points. Okay. So for our analysis, we took all of the methods that we just talked about, and we calculated goodness of fit statistics. So we could easily compare all of the methods to our LOLS model, and then determine, based on our calculations for our simple average and weighted average, which would be the best method to use. So for all the methods we calculated, Pearson's R-squared statistic as our measure of the proportion of variance in the dependent variable that is predictable from the independent variable. We calculated a standard percent error, and that is to understand the difference between the actual and estimated effort as a percentage of the estimated effort. And we also calculated the average percent error, or bias. And bias is a tendency to overestimate or underestimate a parameter. Okay. So for machine learning techniques, when you're going in and about to run the algorithms, you typically define a training and testing proportion of your data set. So 80% of our data set is used to train each of the machine learning algorithms in order for them to learn from the actual data points and use this information to predict new responses. The remaining 20% is used to test the best guesses of the algorithm and help the algorithm to converge upon a solution. And so with this in mind, we decided to calculate the goodness of fit statistics on the in sample, the training set, and the out of sample, the testing set. So while conducting the analysis, we realized that all of the machine learning methods were biased low initially because of the log transformations that we applied during our calculations. And a sample bias correction adjustment was made in line with what is done when calculating estimates using Merlin to correct for this. The simple average was calculated for Merlin, Zimpi, regression trees, random forest, k-nearest neighbor, and support vector machines. So all of the methods were used to calculate the simple average, and the goodness of fit statistics were calculated for those. For the weighted average, we included 4 out of the 6 methods due to some negative weights being produced from Merlin and k-nearest neighbor. So this resulted in us just using Zimpi, regression trees, random forest, and support vector machines for the weighted average. So here are our results. So you see that we have our R-squared, our SPE, and our bias for each of the methods, and then also keep going down to your simple average and your weighted average. And so for the in-sample data, the best single SPE belongs to Zimpi, and then followed by Merlin. So if you can track that. So among the single models, the support vector machine has the highest R-squared, and then Merlin follows close behind. And so the simple average has comparable to the best of any single model, and the same for the SPE. And the weighted average has a similar R-squared, but a much smaller SPE. However, it has a significant positive bias. So we selected the simple average as the best estimate out of all the methods that we have used. And this is for the in-sample data set. And for our out-of-sample, this is the out-of-sample data is a better indicator of how the models will perform when applied in practice. as the coefficients were not influenced by any of the actual data. So for the out-of-sample data, Zimpi and Merlin are the best single models. They both have R-squares in excess of 90%, and the SPEs significantly are better than the other models. The simple average has a negative 50% bias and a much higher standard percent error than Merlin and Zimpi, both. The weighted average, however, has an R-squared and an SPE that is comparable to both Merlin and Zimpi, as well as a lower bias. So we definitely see that the weighted average is better overall than any of the single models that we have presented here. So whether the scenario involves guessing the weight of an animal at a county fair or trying to determine how much a new variant of a combat vehicle will cost, an ensemble approach can often produce a better estimate than a single model alone. For the data that we use, we've shown that the weighted average generally performs better than the single model, and it definitely performs at least as well as a single model. So it is often most common to produce just a single regression estimate. Introducing the ensemble approach can possibly increase the accuracy of your prediction. So we hope that you'll apply some of these methods during the next estimate that you create, and hopefully you'll find that you're able to create a more strong model for prediction using these methods. And we have some backup slides for you as well for you to read on your own. And that's it.
All right, well, we have a question from the audience. I'm just going to go for it. Adam James, sir, you have been unmuted.
All right, great power here. How did you calculate the bias?
It's just the sample bias, you know, on a percentage basis.
Okay, so it is the sample bias because
Yeah, it's just sample bias.
I guess I wouldn't be me if I didn't point it out that some of those methods are in fact biased, most notably ZMP. But sample bias, okay.
Yes, well, ZMP, you constrain the sample bias to be 0, so the sample bias is not 0. It doesn't guarantee that the method is asymptotically unbiased or even consistent, but that's kind of the workaround for getting rid of the bias for MPE.
Okay.
Because that method's always, it tends to be biased high, because when you're trying to minimize y minus f over f, you know, the actual minus the estimate over the estimate, one way to do that is to make the estimates really large, and so that tends to make it biased high.
Right. Okay. Thanks.
Okay. Sure.
Well, that's the only question we got in from the question boxes so far. We're going to turn the mic over to Rick Collins, the ICEAA president. He has a couple of words for everybody. And if you still have some more questions, this will give you an opportunity to send them in. Rick, sir, you have been unmuted.
Thank you, Megan. Can you hear me?
Sure can.
Excellent. Well, good afternoon. First thing I wanted to say is give a hearty congratulations to Cheryl, Christian, Kim, and the rest of the team for the award. Well done. It's always much appreciated when people take the time to write a paper. And so the second thing I wanted to mention to the broader audience here is there's tremendous value, although it takes time, it takes effort in preparing papers for submission. If you get an abstract that's accepted, I think clearly you can't qualify to win an award if you don't submit a paper, but I think that's only one of the benefits. I mean, I think I think you can grow your reputation by writing a paper. I think it's tremendous experience in a learning standpoint to be able to write the paper, struggle with conveying your thoughts in a logical manner. And a paper is something that lives, right? It's something that will be out there when people Google your name and they can read it. So I think there are a lot of different advantages to taking the time to do this. I mean, I certainly can tell you that, Christian's a great example. I mean, he's kind of prolific when it comes to paper writing and winning awards. But at the same time, folks that are way less experienced than Christian have, taken the time and effort to write papers and have found themselves winning awards. So, I highly recommend, both folks that are at the working level and folks who are at the management level here to, do this. It's critical. And I think it's particularly important for the younger folks in the audience to have this opportunity to practice writing and conveying your thoughts. So anyway, congratulations again, and for the rest of you, it's never too early to start thinking about that abstract for next year and planning to actually write a paper rather than just simply presenting. So thank you very much, Megan.
Thank you, Rick. And for anyone who might have missed it, the call for papers for 2021 is up on the website. You can hear it. You can click on it from the main page. We didn't get any more questions during that time, so it seems to me that Christian, Cheryl, and Kim, you guys were you did it. You nailed it.
Thank you, Megan.
So thanks to all of you. Looking forward to hearing everybody next week for our third presentation of the best papers for 2020. And as always, if you need anything from ICEAA, just reach out to us. Thanks, Rick, for chiming in about the value of writing a paper. And I hope everybody has a fantastic rest of their week.